Welcome to our video on the chain rule. This is a pretty powerful rule in calculus that allows you to find the derivatives of functions that are a little more complicated than what we've looked at already. So let's say I ask you to find the derivative of this function. The issue with that function is that we have this power on the binomial. And in the past, we've dealt with something like x plus 2 quantity squared, and we can multiply it out and then apply just our regular old derivative rules to find that. However, finding out what x plus 2 to the fifth power is and writing that as a polynomial becomes exponentially more difficult. So there's a way to find this derivative, and that's called the chain rule. What the chain rule says is that you can take a function, or possibly take a function, and look at it as a composite of two functions, meaning you should be able to find what we call the inside function and the outside function. So in this example, or in the formula for the chain rule, f of x is what we will call our outer function. And then g of x is what we will call our inner function. So revisiting the problem up above, f of x equals x plus 2 to the fifth power, if we wanted to find the derivative of that, so let me rewrite this as the derivative of f of x, and we're going to write f of x as having sort of two parts, okay? So we'll have our outside function and our inside function. I'm just going to write f of x here, but when I write this out, I'm going to write it as my outer function and my inner function. So if we look at our original function here, my outside function could be thought of as being this raising to the fifth power. Okay, so that's what I'm going to call my outer function. I'm raising something to the fifth power. Now we know how to find the derivative of that, and we'll come back to that in just a moment. The inner function is what's inside that being raised to the fifth power. So that would be our x plus 2. So really what we want to think about is when we're finding this derivative, we want to think about how do we find the derivative of the outside function. Let me put that formula back up here so we can see it. How do we find the derivative of the outside function, and then how do we find the derivative of the inside function? So the first part of our formula for the chain rule is to find the derivative of the outer function, not changing the inner function at all. So if I look at this, I want you to think of that outer function as being something like x to the fifth power. Okay, and we know that when we find the derivative of x to the fifth power, it'll be 5 times x to the fourth power. So that's what we're going to do here. We're going to write that as 5 times something to the fourth power. Now that something is x plus 2, and it does not change. So that's the first part of our derivative. The second part of our derivative is just the derivative of the inside function. So my inner function is x plus 2, and we know that the derivative of x plus 2 becomes just 1. So I would multiply this by 1. Now in this case, that has a nice simplification. We could just write that as 5 times, and I'll write it in purple here just to keep things a little consistent. We'll write it as 5 times x plus 2 to the fourth power, and that would be the derivative of our function f of x. All right, let's try maybe a little more complicated one. Okay, so let's find the derivative of f of x. Now, to do that, I have to be able to sort of decompose this into the outer and inner functions. So that's the first thing I'm going to do. Okay, so I'm going to write this as what f of x, kind of using my colors to help me do that. So my outer function is literally think of what's happening on the outside. Or if you were doing order of operations, what you would do as a very last step. So the very last thing I would do if I were plugging in an x value here would be to find whatever's inside the parentheses raised to the third power. So that's going to be my outside function. Okay, so I'm just going to write that something is being raised to the third power. And then that something that's being raised to the third power is what we would call our inner function. So 3 minus 2x squared. That's my inner function. Now, our chain rule says, so to find the derivative, we will first take the derivative of the outer function. So think of that outer function as just being something, that something could be x, raised to the third power. And if I find the derivative of that, we know it's 3 times x squared. So when I write the derivative, I know it's going to be 3 times that something squared. And then I don't change the something. I keep the inner function just as is. And then I will multiply that by the derivative of the inside function. So you can think of that inside function, 3x minus 2x squared. What would the derivative of that be? It would be 3 minus 4x. And that's what we will multiply by, 3 minus 4x. Now, the nice thing is I really don't need to simplify this anymore. Okay, so I can just leave my answer just as is. There's no need to go any further with that. So this would be my answer. The derivative of f of x is just that entire quantity. It's not pretty, and we oftentimes are striving for trying to make something look nice, but it's not always necessary. Okay, let's find another one here. So example 2. We're going to find f prime of x of f of x equals x squared minus 1 raised to the 2/3 power. Okay, and let's just try one more with the powers and then we'll go on to another type. All right, so we have to think about this as our inside and outside function. So if we're going to write this as f of x, I like using colors. You can, literally just write what the inside and outside functions are like I do off to the right here. It's up to you how you want to approach this. But for me, I recognize that, again, my outer function is what I would do last when I'm talking about order of operations. So in this case, that would be the 2/3 power. So my outside function is something being raised to the 2/3 power. And then my inner function is whatever I'm actually raising to the 2/3 power. So that's x squared minus 1. So when I find the derivative, okay, I'm going to find the derivative of the outer function. So think of your outer function as x raised to the 2/3 power. And we know that if we find the derivative of that, it's going to be 2/3 times x to the negative 1/3 power. Now here's where things get a little interesting, and we'll simplify here at the end. But we know what that could be written as because we can rewrite it with a positive exponent and all that kind of stuff. But let's just keep it real simple to start. So I find the derivative, it'll be 2/3 times whatever's on the inside raised to the negative 1/3 power. So I'm going to just keep whatever's on the inside just as is. And then the second part of this is to find the derivative of the inside function. So the inside function is x squared minus 1. And we know if we find the derivative of that, it's just 2x. So I would be multiplying by just 2x. So at this point, we would like to simplify as much as possible. So let's maybe start by rewriting 2x as 2x over 1. It'll make our simplification a little bit easier. Okay, so what I've got is f prime of x equals, okay, I've got 2/3. I'm writing everything that's not inside being raised to the negative 1/3 power next to each other. Times, and then we could rewrite x squared minus 1 quantity raised to the negative 1/3 power as 1 over x squared minus 1 raised to the positive 1/3 power. And then at that point, we can work on just rewriting this as one big fraction. So multiply all your numerators together, you get 4x over 3. Now, you could leave it as the 1/3 power if you'd like. You could also rewrite it using roots. So I could rewrite this as the cubed root of x squared minus 1. If you prefer to leave it as x to the 1/3 power, I'm also okay with that. So this one took a little bit more time to simplify, but when we were done, this is our derivative. Now, if you think about this, if we tried to do this using what we already know how to do, we'd get stuck because we don't know what to do when we have something inside being raised to the 2/3 power. Okay, let's try another one. Okay, we need to talk about rationals because it's something that we encounter quite often. The whole concept of rewriting that we've taken some time to practice is continuing to be a very helpful concept here. So the first thing I'm going to do is I'm going to rewrite this so it's no longer a rational function. I'm going to rewrite it using negative exponents because that allows me to use the rules that I already know how to use. So let's rewrite this as g of t equals -7 and then times 2t minus 3 raised to the -2 power. And again, that's just using our rewriting skills that we've talked about before. Okay, now we could have left it as is, right? And we could have multiplied out 2t minus 3 times 2t minus 3 and used our quotient rule. Hopefully this will be a little bit quicker for us. Okay, so I'm going to rewrite this so I can identify my inside and outside functions. So for g of t, now this time, my outer function, it's a little interesting. Think about what's happening. The best way to describe this is on the outside, right? So on the outside, I've got -7 and something being raised to the -2 power. Okay, that is my outer function. It's no different than if we said -7 x raised to the -2 power. Okay, that x though, in our case, what's being raised to the -2 power is is 2t minus 3. So that would be my inside function. So if I'm going to differentiate, I need to first find the derivative of the outer function. And thinking of it as -7 times x to the -2 power, we know that that would be 14 times x to the -3 power. So I can write that here. 14 times whatever's on the inside raised to the -3 power. So that thing on the inside doesn't change. Then I'll multiply by the derivative of my inner function. So my inner function is 2t minus 3, and I know the derivative for that is just 2. So I will multiply by 2. And then again, we'd like to simplify a little bit. This one's a little bit easier to simplify, I believe, because we don't have to worry about a bunch of different fractions, right? We just have to multiply 14 times 2, because those are outside of what's being raised to the -3rd power, and that's 28. And then we can think of that, well, here, I'll just do it in 2 steps. 2t minus 3 raised to the -3 power. And then finally, we can, adjust for that -3rd power. So we could write this as 28 over 2t minus 3 raised to the 3rd power. And then that's what we have for our derivative. Okay? And this is, I hope you can see, a whole lot easier once you get used to it. This is a whole lot easier to use than, say, your quotient rule. Your quotient rule would have been pretty messy there. Okay, so that's a pretty powerful rule for us to use when we talk about the chain rule. All right, let's just do one more quick example here. And again, the idea of rewriting is going to be important here because I don't know what to do as far as finding the derivative of a square root, but I do know how to find the derivative of something raised to the 1/2 power. So x squared minus 2x plus 1 raised to the 1/2 power is something that I can work with. And then I like to think about them, as being outside and inside functions. So hopefully by now you're recognizing that the outside function is that thing being raised to the 1/2 power, and the inside function is that thing inside. And then using our chain rule, we can find the derivative. So we find the derivative of the outer function. So our outer function is something being raised to the 1/2 power. And we know the derivative of that will be 1/2 times x to the -1/2 power. And we can simplify a little bit here when we're done. But we get 1/2 times that thing raised to the -1/2 power. And that thing on the inside does not change. And then we'll multiply by the derivative of the inner function. So x squared minus 2x plus 1, we know has a derivative of 2x minus 2. So we would multiply by 2x minus 2. Let me kind of separate these a little bit here so we're not getting them confused with our actual derivative. Okay, then our derivative, we can rewrite, and you might be able to do this quicker than I'm going to do right now. I'm going to write everything that's not inside being raised to the -1/2 power all together here. So 2x minus 2 over 1. And then we can think of that x squared minus 2x plus 1 raised to the negative 1/2 power as being over 1 as well. Okay, and then some simple rewrites here. And we might even be able to actually do a little bit additional simplification. So we'd have, in fact, think about it like this. Now we'll just gotta go with it. So we have 2x minus 2 over 2 times 1 over, and then that thing raised to the 1/2 power. Now 2x minus 2 over 2, there's some giant ones that are going to take place there. If you factor out a 2 from the numerator, you're going to get a giant 1. So what we really have is, let's see this. We have x minus 1 left in the numerator times, and in the denominator, we have x squared minus 2x plus 1. And actually, I'm going to go ahead and write that as a radical. Okay, so this part, it's not uber important that you change it into a radical. I would take either answer, either raised to the 1/2 power or written as the square root of x, or square root. So that would be our derivative. And once again, it's probably a lot more powerful and actually easier to use than our quotient rule, which we may have had to use here or in some previous problems. I don't think we used the quotient rule here, but we would have been stuck in this situation because we didn't know how to find the derivative of that. Okay, there's going to be a go formative. Try to work through that as much as you can. When I come back, we can go over any questions you have. We'll have plenty of time to answer those questions, and I will try to monitor your go formative over the next couple days as well. Be good for the sub. I'll see you soon.